Welcome to this special seminar by Stanford Data Science, where our 8 Data Science for Social Good Fellows will present their work on 3 exciting projects with social impact. We're very happy to organize the DSSG program for a 3rd consecutive year at Stanford. And for the first time this year, the program welcomed undergraduate and graduate students outside Stanford, and our 8 fellows were selected among hundreds of students from universities in the United States. And for 8 weeks, our students worked on cutting-edge research projects related to topics like urban inequality, COVID-19, and diversity in education, and also had the opportunity to participate in several weekly educational activities, including seminars, tutorials, and training sessions. So the program would not be possible without the very hard work of many people in this team. So we would like to say a big thank you to the organizing team that also included Chris Menchel, Bala Subramanian, Naras Mishan, Lynn Kiel, Armin Thomas, Kiran Siragur, our financial admins, Debbie Lemos, Margarita Duenas, Kathy Lu at the math department, our wonderful technical mentors, Li Jing Wang, Shilan Al-Zahawi, and Chien Zhao, who mentored and guided our fellows, our faculty mentors, who included Naras, Jackie Huang, Irene Law, and Daniel McDonald, and of course, Stanford Data Science and NSF that provided the funding for the program. So without further delay, we are now ready to begin with the first presentation by the COVID-19 team. Please use the Q&A chat to ask your questions. Each team will have about 20 minutes to present, and then we'll have about 5 to 10 minutes to answer questions at the end of their presentation. COVID team, if you're ready.
Great. All right, thank you so much for a great introduction, Phaedra.
Thank you. We can see your slides.
Awesome. So welcome to the final presentation for the COVIDcast project. Before we get started, we want to introduce our team first. So we have Taha, who recently graduated with a computational sciences from Minerva University. And my name is Michelle. I recently graduated from Columbia University with Masters in Public Health. And we were both DSSG fellow for the summer. And Shilan was our technical mentor. She is a PhD student at Stanford University Graduate School of Business. And Naraz and Daniel were our faculty mentors. Naraz is from Stanford University and Daniel is from University of British Columbia, Canada. And Naraz and Daniel are both associated with Delphi. So before we dive into the details of the project, we wanted to introduce a little bit more about the Delphi Research Group. The Delphi Research Group is at Carnegie Mellon University and is one of the 2 influenza forecasters in the United States. And the group's goal is to develop the theory and practice of epidemiological forecasting with a long-term vision of making this technology as universally accepted and useful as weathercasting is today. Prior to COVID-19, the group also worked on forecasting for influenzas, dengue, and norovirus. Right, so since March 2020, when COVID-19 really hit the United States, the Delphi Research Group has maintained the largest public repository of real-time indicators of COVID-19 activity in the US. And every Monday, the Delphi COVIDcast generates and forecasts of cumulative COVID-19 cases and deaths in the US. And these predictions are reviewed by the team at Delphi, and they're sent to the CDC COVID-19 Forecast Hub. And this forecast hub maintains up-to-date record of dozens of leading infectious disease modeling teams from around the world, and for COVID-19 cases, deaths, and hospitalizations in the US. And the prediction models, the forecasters are used like this to create forecasts by the CDC as shown in the plot here. And for this plot specifically, it's showing the new cases forecast. And this plot is from the CDC website. And as you can see on the left bottom corner, there are about like dozens of different forecasters. And these show how like predictions for August 1st and onward. So for a couple of weeks, you can see the plots, what it's forecasting. And you can also notice that there's a huge fan, like there's a huge array of different forecasters. And the reason that each forecasters have different results is because they rely on different models. So some are time series models, some are neural net models, and they also they may also use data history in many different ways. And these plots are really important for epidemiologists and public health officials because they help us evaluate forecasters. That helps them gain insights into the performance of their forecasts and learn and lead to more accurate forecasting and understanding of future epidemics. And also these forecasts help us accelerate the recovery of lives and communities that have been impacted by COVID-19 while also investing in the science behind the science to mitigate the future damages of epidemics. So through these evaluation tools, Delphi would like to know how does our forecaster do compared to others? And it'll also help them assess new forecasters before they are deployed. And it also shows, are there areas or periods of time that needs to be focused and that needs to be improved? So our main project during the fellowship involves the creation of a report that answers these questions. So for the main goal for our fellowship was to develop tools for comparing and evaluating COVID-19 forecasters. And our deliverables included an interactive parameterized report that evaluates and compares the performance of several COVID-19 forecasters for cases, deaths, and hospitalizations in the US. That is also downloadable. And the users can automatically generate a report according to their chosen parameters. And the parameters include the number of epi weeks ahead for forecasts and also specific forecasters that they want to compare to, and whether or not to use a colorblind safe palette for the plots. And everything was uploaded to a GitHub repository with fully documented codes and vignettes at the end. And please note here that a template was already created by the Delphi team to explore forecaster performances on COVID-19 deaths. And our task was to improve this template and add certain features that will help them better understand forecast performances. And we also added new outcomes that are predicted above and beyond COVID-19 deaths, including cases and hospitalizations. And we'll share about this more in a little bit. So we want to discuss our three main outcomes of interest before we go into more detail. They were COVID-19 cases, deaths, and hospitalizations. And the sources of these forecasters were based on USA Facts and by a team and the team from Johns Hopkins University for the cases. So for the cases, it was defined as number of daily confirmed cases reported by the state and local health authorities. And it reflects only cases reported by the health authorities. So it may not be directly comparable across regions with very different and different testing capacity or reporting criteria. COVID-19 deaths had similar data sources as well. They were also from USA Facts and Johns Hopkins University. It reflects official figures confirmed by health authorities. So the data may not include excess deaths that were not confirmed by health authorities due to COVID-19. Hospital records were a little bit different. Delphi received from their health system partners related to COVID-19 hospital admissions that were derived from ICD codes found on insurance claims. So using this data, Delphi was able to estimate the percentage of new hospital admissions each day that are related to COVID-19. And these numbers were, estimates are based on admissions by patients whose data were accessible by certain insurance companies and insurance admissions. So not all currently hospitalized patients who have COVID-19 related diagnosis might not have been included in this record. And the hospitalization record is especially important with the increased cases of hospitalization due to new variants.
Thank you, Michelle. So as Michelle mentioned, the task that our group has been amended was basically to compare the performance of forecasters. And to do that, we have to define specific metrics that we have to compare them by. So here in this slide, we're introducing the 3 metrics that we are evaluating forecasters by. So the first one is a weighted interval score, which is a proper score that approximates a continuous ranked probability score. It can be interpreted as a generalization of the absolute error to probabilistic forecasts and allows for a decomposition into a measure of sharpness and penalties for over and under prediction. Coverage, or like 80% coverage, is estimated on a particular date by computing the proportion of locations, it could be states or counties, for which a forecaster's interval includes the actual value on that date. A perfectly calibrated forecaster would have individuals intervals empirical coverage matching its nominal coverage. And in the plot, I think we're going to mention the plot in a couple slides. This corresponds of being on the horizontal sort of black line that's drawn on 100%. Overconfidence corresponds to being below the line, underconfidence corresponds to being above the line. And the third metric, which is the most straightforward one, is just an absolute error. So it's just the gap between the forecasted sort of point by a specific forecaster versus the actual ground truth that's been reported for a specific COVID signal. Could be deaths or hospitalizations. So the limitation of the current reports, or like the report that we've been given in the beginning, is that it was too specific, meaning that there were specific choices that have been made in terms of plotting and in terms of parameters that have been chosen. So there wasn't a lot of sort of room for changing the parameters or exploring different plots. The second limitation was that it was API based. It was slow in knitting RStudio, meaning you have to make an API call to retrieve the data, do the computation of these sort of parameter metrics that we've mentioned, and then get your knitted report. And it was also unable to run reports in case the API went down for whatever reason. Usually this happens when new data come in every week, that the API doesn't really sort of get data properly. The third limitation is it was, as I mentioned in the beginning, unable to be personalized, meaning that you cannot make a lot of choices in terms of parameters. And the last limitation was visually unappealing. Many plots were rigid and there was no interactivity there. There was also a limitation of how many forecasters you could fit in a specific plot. So our architecture for a generalizable plot or like a report was basically to start with a template that is very general. And then the user basically will have the ability to make choices in terms of parameters. For example, what forecasters you're interested in, how many weeks ahead as a horizon you're interested in forecasting, and so forth. And by combining the two, you will have a modified error markdown, and then you will end up with a knitted report with the specific choices that you've made. So this is basically the architecture that we've designed our report over. So functionality-wise, this is basically what it looks like in first step. So you start by generating like a template that you're interested in. It could be a template for COVID cases, for hospitalization cases, or deaths, with the parameters that you picked. As I mentioned earlier, there is a bunch of forecasters that you could pick, and the primary forecaster, as well as the horizon that you will forecast for. And that's shown in the window on the left side. On the right side, you could see the cover of the report, beginning with the title, a small abstract, and reiterating the choices that you've made as they're highlighted in the bottom. Specific dates that you're forecasting for and the forecasters that you picked. So this is basically the first step. Second step, basically, as we mentioned earlier, we wanted to add some interactivity. So exploring, we added a set of interactive graphs sectioned into tabs. As you can see here, each tab is specific for, each tab contains a specific metric out of the 3 that we've mentioned. So you could explore weighted interval score across different forecasters and also across different forecasting horizons. It could be 1 week ahead or 2 weeks ahead. And you could switch tabs to see how each forecaster is doing under a specific metric that you pick. Next, you could call it step 3. Although we made this report generalizable, we also wanted to make it an option to always be able to retrieve the data. So we have 2 sort of data that we work with. The first one is the evaluation data, meaning that after you get your forecasters and you have the predictions, you compute a specific set of metrics, and you could download that data, try to sort of, for example, replicate the graphs that we've plotted. You could also get the raw data, just predictions, without any evaluation, and that would allow you to, for example, try your own metrics and see if, for example, you sort of care about a specific metric other than the 3 that we've mentioned. You could also add that and have the raw prediction data to sort of compare these forecasters' performance. So the option to download data is always open, and it sort of opens the door to many possibilities for people to explore forecast evaluations. Next is, so we've made a choice when plotting to sort of have the option to have it colorblind safe. So you could make this choice in the beginning, have your plots with a color palette that doesn't really show them to be very close in terms of color for people that are colorblind. So this is always an option that you could explore. So for example, in this specific plot, the y-axis is the weighted interval score, and the x-axis is the weeks ahead that you're forecasting for. You have a set of forecasters on the right side, and you sort of could see, for example, in the weighted interval score, the lower the value, the better. And you could see, for example, here that the MIT forecaster is not doing as well. The MIT forecaster and the CU forecaster is not doing as well as the rest. So this is basically an example of how you could change the color palette to make it colorblind safe. Another detail that we really cared about was, as we mentioned earlier, evaluating forecasters could be happening in 2 dimensions. You could evaluate them sort of in a temporal dimension. So for example, how well they do in terms of forecasting if you forecast 1 week ahead, 2, 3, and 4. So for different horizons, how consistent they are performance-wise. And we also wanted to contextualize this data geographically. So maps are a very sort of informative way of showing how forecasters are performing in different states. A forecaster can be doing well overall in the US, but they could have some a forecaster could be doing well in the US overall, but they could have some sort of specific regions or states that they were not doing well in. So there's the example in this plot where you could see that the COVID hub ensemble is not doing very well in the state of Kentucky, that is shown in yellow in the second map, compared to the other forecasters. And that's like a very sort of intuitive way to sort of single out if a specific forecaster is not performing well in a specific state. Again, just to reiterate, here in the state of Kentucky, since it's colored yellow and yellow is high in the scale, it means that it has a high weighted interval score, which means that specific forecaster is not doing as well as the rest. Another detail is that these maps are also sectioned based on the metrics. So you could also see that the tabs on the top are also for different metrics. So if you click on the next tab, you will see also maps of the United States with each state colored based on the performance of a specific forecaster in that state. So you have like a whole array of metrics that you could sort of explore and see how forecasters are doing in specific states. And in the next slide, these are basically trajectory plots that we sort of generate based on the primary forecaster. A trajectory plot basically will have 4 different horizons of forecasting, like projected into like the actual COVID count. So here in the black curve or the black line, this is like the actual value of COVID deaths, and the purple lines are basically like 4 different horizons of forecasting that the primary forecasters is sort of like is evaluated against. And in the tab that we sectioned here, it's basically like 4 regions of the United States that we sectioned in different tabs to make it easy to sort of switch between states and not be overwhelmed with 50 plots in the same page. So in the, I think this is it for trajectory plot. Next is plot 18.
Right. So as Taha mentioned here, there were some limitations with the original report, the original template. So in order to address these issues, some of the solutions we've offered during our fellowship was to use parameters and helper functions that can change the markdown parameters and include a diverse choice of options for users to select. Also, in order to address the API issue, we now use download of formative data from AWS bucket directly, and also and prediction data frame. And to address the personalization issue, now we have added better interactivity to the plots, so people can see it better, and they can also download data to personalize the forecast evaluation tools. And also lastly, to address the visualization issue, we can now see the plots in organized tabs for easier navigation. So to wrap up, during the fellowship, we were able to produce a couple of templated markdown files, our scripts for manipulating markdowns, example reports, and a GitHub repository that includes all of our work and vignettes. And for the future, we hope that if time permits, that Delphi can use Shiny app that generates the report with the click of a button, and also have a report that shows county-specific forecaster performances. And lastly, Docker solution for batch generation of reports. Amazing. So that wraps up our presentation. And we want to express huge gratitude to our Delphi, to our mentors and Delphi group for making this possible for us. Taha and I, we both learned to adapt and be flexible throughout the course of this project. And it has been very exciting and one-of-a-kind learning experience for the both of us. So thank you, Shalon, Naraz, and Daniel. And now we are open for any questions and feedback.
Yeah, thank you, Michelle and Taha. So there were several questions in the chat. There's still one question that has not been answered. How were then sample weights chosen, and did you use a super learner type of method, or did you use the CDC or Hawkins data retrospectively to validate then sample learner? The question is in the chat.
Yeah, I think the ensemble was part of the set of forecasters that were already in the AWS bucket. So it was not, we didn't make any choices in terms of getting the ensemble. We were mostly focused on evaluating these forecasters. So yeah, I'm not quite sure about the weights, but it's not something that we were really working on. We were more concerned about the evaluation of ensembles. Probably, I'm not quite sure, maybe Daniel might know a little bit about the ensemble, but yeah.
In the meantime, the audience can add more questions in the chat. So I have another question myself. So you mentioned at the beginning that you were interested in understanding in periods of time that you were doing better or worse. So did you observe any interesting examples or insights from the data?
Right, that's a really good question. I think we can go back to the slides. I mean, here, like when we use the maps, like we can easily identify states with pretty high weighted interval score to identify, and like, you know, we want to look back at the data and see why that's so. I think also with graphs, like these plots show dates from like July 2020 to July 2021. So that's over a course of the past year. We were able to see how the forecasters are doing. And the lower the number, the better it is. So here we're easily able to identify the forecasters that are not doing as well. So, I mean, I think like an interesting learning thing is that, you know, we are mainly focused on CMU time series, which is the Delphi forecast model. And, you know, it's doing really well compared to other forecasters. So those are the things that we're able to learn from it, that our forecaster is, you know, performing well compared to others. And if we were to add new forecasters, like how, you know, we're able to evaluate how that would do as well.
Great.
Just to sort of, sorry, I wanted to add something of.
Yeah, sure. You have like half a minute.
Okay, yeah, just in terms of like kind of challenges that we sort of might have encountered in data. If we go to slide 17, Michelle. So in trajectory plots, like we'll face like a lot of instances where there are like anomalies in data. It could be data entry or something like that, which sort of like mess with forecasters sort of do. For example, you can see here Delaware has a huge spike up from the usual in the lower left plot. Like there are sort of anomalies in data that could sort of distort the way that forecasters perform. So these are like challenges in data entry that have to be investigated. I think the Delphi group, like before in the old report, they had like manual corrections that they had to do to bypass that. But that's like one challenge that could hinder the way our evaluation of the forecasts would go. So yeah, that's one challenge.
Awesome. So thank you again for the great presentation. Feel free to answer any remaining questions in the chat. We are now ready to move to the second theme, which is about neighborhoods and well-being. So whenever you're ready, please share your slides.
Sure, I will share it right now.
Great, we can see your slides.
Mm-hmm. So good morning, everyone. Welcome to our presentation. We are the second team of the 2021 DSSG program, and today we'll be talking about our project on measuring the spatial temporal change of physical conditions in neighborhoods with street view imageries. So spatial means across cities, and temporal means across time. Basically, the project is about measuring the change of physical conditions of buildings at different neighborhoods at different years and across different cities. First, I would love to introduce our amazing team. We have 3 student fellows, Daniel, me, and Evelyn. Daniel just graduated from Stanford undergraduate studies and is returning for the Master of Statistics program. I am Tingyan. I'm a rising senior student at Vanderbilt University studying computer science, math, and economics. Evelyn just graduated from Cornell University with a Master of Computer Science. Our technical mentor is Li Jing. She's a 4th-year PhD student at the Department of Geological Science at Stanford. And our faculty mentor is Dr. Huang. She's a professor in the sociology department at Stanford. So to start with, let's talk about the motivation behind our project. Previous research shows that the presence of physical disorder, poorly maintained properties, and vacant lots in different neighborhoods can negatively affect neighborhoods' physical and mental health. It can also attract more crime and disorder. This will lead to neighborhood disinvestment. In addition, many studies related to residential well-being have shown that the greener the urban land, the happier the residents. So clearly, neighborhoods environments plays a significant role in shaping the well-being of individuals and communities, which will consequently contribute to the inequality in the United States, considering some of the negative effects mentioned before. However, very few studies have investigated this process mainly because collecting data on the physical conditions of neighborhoods, especially across neighborhoods and cities and over time, requires extensive time and labor costs. Therefore, to address this challenge and also contribute to the current understanding of the potential effect of the neighborhood environments, we collaborate with Changing Cities Research Lab at Stanford University to identify the physical conditions of neighborhoods environments at a larger scale. But how exactly do we make our measurements into a larger scale? And how do we use any modern technology to get the street view images across multiple years? So the approach we use to directly observe the physical, social, and economic characteristics of neighborhoods is called systematic social observations, SSO. So when the idea of SSO first came around the 20th century, social scientists using SSO relied on street audits, where observers walk around the street and fill out the survey instruments. Then in the 1990s, a research team led by Robert Sampson using camcorders to record blocks and have coders fill out the surveys after, which greatly reduced time and labor costs from fielding survey takers. Finally, in 2009, the Google Street View imagery was publicly released. It contains millions of street view images, and GSV was publicly released in the United States, which further reduced costs by providing recorded street view images and across multiple cities over the years. And this is also how we got our images. So with the images obtained from the GSV, our team aims to improve the understanding of the role of physical and environmental neighborhood conditions in structuring inequality in well-being in different US cities. By doing so, this project aims to inform solutions that can inform the well-being of residents and reduce inequalities. So our project goal would be to use the deep learning approach to visually identify upkeep, blight, building materials, and greenery layouts around buildings from Google Street View images. Furthermore, we will use crowdsourcing and computer vision techniques to quantitatively measure physical aspects of the urban neighborhoods environments that have been linked to different well-being data sets in the last 10 years. Our analysis also across multiple cities, including Detroit, Boston, and LA. We link these measures with the existing data on individual and community well-being to analyze how the well-being changes over the time and how the physical and environmental conditions have affected the well-being of individuals and neighborhoods over time. So to get a taste of what the Google Street View images look like, here is one example of a building in Detroit from the year 2007 to 2017. So with GSV, we were able to navigate a single location in 360 degrees going all the way back to 2007 and obtain images of the same building every 1 to 3 years. GSV images were collected by driving, paddling, and walking around and capturing images with special cameras. The cameras were able to simultaneously collect images in multiple directions. And as of 2017, GSV covers 10 million miles of images in 83 countries. This allowed us to navigate the street view over 10 years and understand the physical conditions in different neighborhoods over time. Now, as we have seen an example of the GSV image, let's delve into our label data. So our data source is mainly the images grabbed from the GSV spanning from the year 2007 to 2017, with the images taken every 1 to 3 years and 50 million images in total. Our lab has collected and pre-processed this data. Then to create training data, we use a crowdsourcing platform called Amazon MTurk. So we basically use MTurk as a survey and hire MTurkers to generate our training sets. As you can see, the 2 images shown below is an example of our second stage survey. So MTurkers were asked to compare the 2 images and answer which one has a better upkeep. We use this method because we found that pairwise surveys have a more reliability in producing comparisons across a set of objects. And to make our training data more robust and comprehensive, each image is compared at least 18 times to produce a stable estimate. And with Amazon MTurk, we can capture tens of thousands of comparisons in a single day. And eventually, our training set consists of around 3,000 images from Boston and 4,000 images from Detroit. So after we receive the comparison of the images, we apply the true skill score algorithm to basically rank them and apply a threshold to classify each image into a class. And we have 4 classes in total, class 0 to 3. Now you might have noticed that our images have both a true skill score, which is a continuous label, along with a discrete class. And the reason why this was the case is because originally our problem we set up our problem as a classification task. And we were asked to predict different levels of upkeep ranging from the 4 different classes. And the way that these classes were derived is illustrated here on the slide. So we basically generate the scores from the comparison results done by the MTurkers, then apply the true skill scores qualitatively and to qualitatively analyze to create the various cutoffs to create the 4 different classes. And then the model was used to train to predict those 4 classes. Now, what we were thinking is that maybe it might make more sense to instead stop at the step 2 and have the model instead directly predict the true skill score. So in that case, we would be shifting the problem to a regression task. And the main reason why we felt this might make sense is because of the interpretability of the classes. Also, we realized that the higher the class number, the better the building upkeep and the lower the true skill score. Now let's look at some of the example images to better understand what I just did. So here is a list of example images of the output true skill scores and classes. So the top row is the Boston image and the bottom row is the Detroit, the top row is the Detroit image and the bottom row is the Boston image. So let's take the first image as an example. The first number 0 is a true skill class. The second number 33.54 is a true skill score. So, and as you can see, we have all 4 classes 0 to 3 in this screenshot. And you might have realized that as we go from left to right, we can see that the true skills gets lower and we got a higher class number and got a better upkeep. And as a visual inspection, we can see that Boston tend to have a better upkeep compared to Detroit. And you can tell that from the first 3 images. And to further analyze this possibility, we generate a bar chart to visualize the percentage of different classes for the 2 cities. So here is a bar chart that visualizes the percentage of classes for the 2 cities. And the x-axis is the name of the city. So we have Detroit and Boston here. The y-axis is the percentage of the images that belongs to a certain class. And we notice a problem of class imbalance here. And we can clearly see that Boston has a better upkeep because we have much more classes 2 and class 3 in Boston. Detroit has 7.6% of class 0 images, whereas Boston only has 0.0675% of the class 0 images. And also Boston has over 12.6% of class 3 images, whereas Detroit only has 0.25%. Now I will pass to Daniel to talk about some of the challenges we face and how we resolved them.
Yeah, so first, as a quick recap of what our training data looks like, could we go on to the next slide? Yeah, so a quick recap of what our training data looks like. We have around 3,000 Boston images and around 4,000 Detroit images that we're going to be using for our training set. And again, each image has a discrete class, so a label from 0, 1, 2, or 3, and it also has a true skill score. So using this data, we want to be able to train a model that predicts building upkeep. But there are two main challenges we had when we were trying to build this model. So the first was deciding whether to pose this problem as a classification or as a regression task. And then the second challenge we had was getting the true skill scores aligned across cities. So first, as Tina mentioned, our images have two types of labels, a true skill score and a discrete class label. And the reason why this is the case is because in previous research from our lab, we were looking at levels of trash in urban environments. And we were measuring trash using different classes, such as no trash, a little bit of trash, a lot of trash, etc. And so when we first started off trying to detect building upkeep, we used a similar method where we were trying to predict discrete classes of building upkeep. But what we felt is that once we switched our task from identifying trash to identifying upkeep, using classes to describe upkeep wasn't as easy to interpret as before. So as an example, here we have 3 images from 3 of the classes. So if I remove the labels and I ask you to look and tell me which class each of these images belong to, it might be pretty hard for you to figure out which one belongs to which class. You might be able to tell me which image looks better than the others, but it's not super clear that they're so different that they belong in different classes. And so what we decided is that instead of predicting these discrete classes, we would instead directly predict this continuous true skill score. And so because of that, we shifted our problem from a classification task to a regression task. So that was our first challenge. Our second challenge actually came from the fact that we were using this true skill score as our new label to do this regression. So one important thing to note about these true skill scores is that the Boston data and the Detroit data aren't on the same scale. The reason why this is the case is because, as we mentioned earlier, true skill scores are derived by comparing pairs of images to see their upkeep. But one thing to note is that these comparisons are only done within each city. So what that means is that images from Boston are never actually directly compared to images from Detroit. And so that means that when we get the true skill scores, a label of 25 in Detroit might not reflect the same level of upkeep as a label of 25 in Boston. And this is an issue because if they're not on the same scale, then we can't use the data from both cities to train the model. And because of this, we needed to design a way so that the true skill scores from Detroit would line up with the true skill scores from Boston. But one piece of information we can actually leverage is the fact that while the true skill scores aren't comparable across cities, the class labels of 0, 1, 2, and 3 are comparable across cities. The reason why this is the case is because, as we mentioned earlier, the classes are derived by qualitatively thresholding the true skill score. And because of that, the classes were explicitly designed so that they should reflect the same level of upkeep across different cities. So in this case, a class label of 0 in Boston should reflect the same level of upkeep as a class 0 in Detroit. So using this information, we can align the true skill scores by looking at the boundary true skill scores of each class. So let's walk through an example here. So say we're looking at class 0 images from Boston, and let's say that the range of true skill scores for those images are from 17 to 19. Now let's look at the corresponding class 0 images from Detroit. Now, in a perfect world, these class 0 images from Detroit would have the same range of true skill scores that we saw in Boston, but we know that's not the case yet since they're not on the same scale. So let's say, for instance, that the range for Detroit is 16 to 18. Now, what we'd like to see is for the range of the true skill scores in Boston to line up with what we see in Detroit. So what we can do is we can just move those scores over using a linear transformation. And so in this case, if we wanted the range in Boston to line up with the range in Detroit, we can take all the class 0 images in Boston and just subtract 1 from their true skill score. And by doing so, all the class 0 images from both cities would have a range from 16 to 18. And then if we do this process for class 1 and class 2 and class 3, we can essentially create a piecewise linear transformation to turn the scores from Boston onto the same scale as Detroit. So now that we figured out exactly how we want to use these images and their labels, we can now jump into the model that we built. So for our model architecture, first we take our Boston data set and align the true skill score labels to our Detroit data set, as I mentioned before. And then we use that combined data set to fine tune our Resonant 18 model that has already been pre-trained on ImageNet. And then finally, we get a model that we can feed new Google Street View images from a variety of cities, and we can get out a true skill score prediction that reflects the building upkeep of that image. And using this model, here are the results from our validation set, which includes images from both Boston and Detroit. So on the x-axis, we have the actual score, the true skill label, and on the y-axis, we have the score that our model predicted. The red line represents a perfect model where the ground truth and predicted score are exactly 1-to-1, and you can see that our model also follows that slope pretty closely. And overall, this was our best performing model with an R squared of 0.484 and a mean squared error of 4.487. We were also curious about how this regression model would hold up if it were forced to predict classes instead. And so to do this, we applied the cutoffs we originally used to turn the true skill scores into classes, except this time we directly applied those cutoffs to the predicted scores. So if you look at the graph, there's now these red squares that are overlaid. And these squares represent the regions where images have the correct classification result based on this thresholding. So you can see that overall, it does pretty well in general, especially for the majority class, although it definitely still has some issues with some of the minority classes in the top right, since they have regions that are a lot smaller and therefore easier to misclassify. So to see how this model is performing on these minority classes, we also compared our model to a naive baseline, where the naive classifier randomly predicts classes based on how often the class shows up in the data set. So if a class shows up 70% of the time in the data set, every time the classifier sees an image, it'll have a 70% chance of randomly picking that class. And the metrics we used were precision and recall. And just as a mental refresher on these terms, the precision of a specific class, let's call this class X, for instance. So the precision is the true positives. So the number of class X images you correctly classify as class X, divided by the total number of images that you predicted as class X. So the precision kind of measures when you predict class X, how many of the images are actually from class X. Meanwhile, the recall of a class is the true positives divided by the number of images that have a ground truth label of class X. So the recall kind of measures how much of the class X did you actually correctly classify. And so you can see that for the minority classes in our precision recall here, which are the minority classes are class 0, 1, and 3, while the naive model only has a precision and recall at 0.1 at the very highest, our model does significantly better in both the precision and recall for these classes. And so it suggests that while our model isn't perfect at predicting these minority classes, it's definitely doing a lot better than chance. And now I'll turn it over to Evelyn.
Thank you, Daniel. We also did some visualizations of the results. So here, as you can see, we plotted the actual and predicted scores from the Detroit validation set, averaged by block group, and we displayed them on a map. So on the left, we have the actual scores of block groups in Detroit, and on the right, we have our predicted scores. Brighter colors correspond to higher levels of blight, while darker colors correspond to higher levels of upkeep. And even though the predictions for individual buildings are more noisy, if you look closely at both maps, you'll notice that the predictions are similar to the average actual blight levels in each block group. We also visualized scores from the Boston validation set by block group. And once again, you can see that the actual and predicted scores are quite similar to one another. Notice that the colors in Boston overall are a lot darker than in Detroit, indicating that Boston has a higher level of building upkeep than Detroit. This is in line with what we've observed in the past. So we've talked about training the neural network to predict upkeep levels for buildings in Google Street View images. Now, I'm going to talk about how we use the neural network to measure upkeep levels over time in Boston. We did some time series analysis on Street View images taken between 2007 and 2017. Since there were far fewer images for even numbered years than for odd numbered years, we grouped consecutive years together. So for example, we grouped 2007 and 2008 together. We took the average of the predicted true skill scores for each block group during each 2-year period. Going from left to right, most of the block groups shown in the maps get brighter between 2012 and 2017, indicating that the average level of blight in Boston has gone up and then down. Sorry, they got brighter between 2008 and 2011, and then darker between 2012 and 2017, which shows that the average level of blight has gone up and then down. Some block groups, like the one circled in green, appear to have undergone an increase in blight between 2012 and 2017. However, we only have data for 2 buildings in this block group, so this trend is very uncertain. So why did Boston become more blighted between 2008 and 2012? Well, an important event in the global economy that occurred around this time was the Great Recession, which resulted in higher unemployment and poverty in the United States. The recession may have had a negative impact on well-being. For example, one study found that suicides increased in countries with higher levels of job loss after the recession. So we decided to look at how the changes in urban blight in Boston over time might be related to the Great Recession by seeing how the predicted true skill scores for the time series data compare with median household income. Once again, higher true skill scores mean higher blight. These error bars are 95% confidence intervals, and they don't overlap. So we can see that the changes in average blight scores in Boston over time are significant. And they're associated with opposite changes in median household income on the right, about 2 years later. So to conclude, we trained a deep neural network to measure the level of upkeep in a neighborhood using Google Street View images of buildings. We call this technique systematic social observation at scale. Our neural network can identify changes in average building upkeep at the block group level in different neighborhoods and cities. And finally, our time series analysis shows how changes in building upkeep in Boston track overall economic trends, specifically the Great Recession and the subsequent recovery. In the future, we hope that our project will lead to a better understanding of how neighborhood upkeep in cities changes over time. Specifically, we hope to extend our time series analysis to other cities like Austin and Detroit. We also hope to better understand the relationship between neighborhood upkeep and well-being, using metrics such as crime rates, physical and mental health, income, and subjective well-being. And finally, we hope this research will lead to recommendations for policies that can reduce inequities in well-being. For example, we might recommend that cities conduct targeted greening and cleaning initiatives to reduce urban blight if we believe that they will lead to better community well-being. Thank you all for listening, and we look forward to taking any questions you might have.
Thank you, team. There is already a question in the chat. Evelyn, I don't know if you're going to answer this live.
Yeah, I'd love to take this question.
So to repeat the question, sorry. Some of the images have trees and shadows. How would these nature features affect the score? Thank you.
Yeah, so sorry for the interruption. So to answer this question, we have noticed that greenery surrounding the buildings can affect the scores that are predicted by the neural network. So for example, we looked at images of the same house that were taken at slightly different camera positions, and 3 of the images showed mostly had the house in view, and one of them had the house, like half of the house shown to one side, and then the other half of the image was, you could see like the yard or the backyard on the side of the house, and the model predicted a higher level of blight for the image with more of the yard visible, even though the house looked substantially the same. So yeah, like the presence of greenery can actually throw off estimates.
I have a quick question. I was wondering why your team chose to compare Boston and Detroit over any other cities.
Yeah, so I can answer that. So right now we only have the data for Boston, Detroit, and LA. So we chose Boston and Detroit is because LA images, we have around 1.8 million images over the time series. And it would be taking a very long time to get those images processed. And also we had some trouble with the Microsoft Azure to move off the images to Azure. So that's why we did Boston and Detroit.
Thank you.
Other questions by the panelists or the audience? I have a quick question. First, I want to say that I found like the insight about the relationship between well-being and building upkeep in Boston very interesting, especially the connection with the recession. So I was wondering how much did you trust the labels that the Amazon M trackers provided? Like, did you notice any consistent errors or patterns in the comparisons you gave?
I'll take this one. Yeah, so we are kind of skeptical of the labels that we're given because blight is a really broad and vague concept. So we've actually started collecting new data via MTurk, where we're breaking down the concept of blight into more specific indicators, such as unkempt greenery, off the top of my head, cracked siding, deteriorated roofing, and yeah, like just specific things that people can identify visually, instead of having all of those things conflated together in like a single metric of blight.
Yeah, and I just want to add up to answer Ming's question. So here is what Evelyn just talked about. So we analyzed this before. So you can see this is one image over the year. And we can see that like on the 2011, this one with greenery has a significantly higher true skill score, which indicates a lower upkeep. And also another issue we found is that the lightening of the images also matter. So we can see like the image on the bottom left has a smaller true skill score compared to the top left and also the bottom right, even though they basically look under the same condition to me. And also regarding your question about the area deprivation index, we did not compare that. We did not compare that. And also, me and Evelyn are still working on this project, so we're looking forward to compare our results with more well-being analysis. So that would be definitely one thing we will be looking at. And thank you for mentioning.
Thank you. I think you have also answered all the questions in the chat. So thank you again for the presentation. And we are now ready to move to the third and final presentation by the SFUSD team. Great, we can see your slides now.
Awesome. Hi, everyone. We're operationalizing equity tiebreaker in the San Francisco Student School assignment. So just some introduction. I'm Ria Berry. I'm the student fellow. We also have Gabriel and Juan with us as student fellows. Our technical mentor is Chun, and our faculty mentor is Irene. And so we're going to start off with some background of some historical context and further background of the student assignment policy process. So the San Francisco Unified School District is a very diverse and large district. However, many neighborhoods and schools within SFUSD have a history of segregation. Student assignment policies have sought to desegregate schools since 1971. And since 2002, SFUSD has used district-wide choice to work towards integrating schools. This is all based on an underlying principle and belief that all students deserve equitable access to quality education and that all students should benefit from the diversity of SFUSD. Diversity has been shown to reduce bias, counter stereotypes, foster meaningful relationships across different communities, and to close achievement gaps across racial and socioeconomic lines. And this is some more insight into the student assignment algorithm that I mentioned. So how it works is that students list their preferences for schools. So students and families come together and create a ranked list of their preferences. So if the number of applicants to a given school exceeds the number of available seats, tiebreakers will be used to give preferences to certain applicants who are more disadvantaged or who deserve the tiebreaker. So the existing tiebreakers are sibling tiebreakers if your sibling went to that school, pre-K if you attended pre-K in that area, and the Ctip1 tiebreaker, which I'll delve into later on. And a lottery system is used to break the remaining ties. So as you can see on this diagram on the right, this is what many of you might know as a deferred acceptance algorithm. So in round one, students' first choices are tentatively matched to the schools that want them or desire them most. Schools can reject them later if a student higher on the school's list can be matched in future rounds. So in round two, unmatched students are paired with their next choice. So if you look at the second column, you can see that school one accepts student B, but rejects student D, who's lower on its preference list. And then in round three, student G and I are matched their third choices, and student D, who was rejected before, is matched to its second choice. So all of the matches are now set. And this is some insight into the underlying algorithm that how our system operates. Yeah, and I mentioned before the Ctip1 tiebreaker. So just some more context on that. How the tiebreaker works is that it is awarded to students living in census tracts with the lowest average test score. And those are test scores from the 2006 to 2009 CST English Language Arts exam. This has been running from 2011 and it will run up to 2022. So it has been in place for a while, but students and families and the district has seen over time that the Ctip1 tiebreaker is not sufficiently predictable, transparent, or flexible. Furthermore, they've seen that the choice patterns in the assignment preferences that I walked through before tend to exacerbate racial and economic segregation rather than reversing this historical trend of isolation in San Francisco. And lastly, people don't quite understand why the district is using test scores for priority rather than diversity categories. Which leads us to the 2018 resolution for a proposed policy. So how this policy works is, number one, it seeks to restrict choice to geographic zones. Number two, redesign the Ctip1 tiebreaker as what we will call the equity tiebreaker. And number three, use diversity categories to reserve seats proportionally at each school according to zone demographics. And so overall, this works to improve school diversity and create more of an equitable access to all students for their education. Specifically, some of the underlying values that we're hoping to work towards are diversity, predictability, and proximity for students and families. So the students that the equity tiebreaker is seeking to target the most are those that come from historically underserved groups and communities who we hope to give a priority in school assignment so that they have better and more equitable access to the education in San Francisco. So currently, we're defining focal students at the intersection of two underserved groups. So on the racial lens, we have African American, Latinx, and Pacific Islander students who we'll refer to as AALPI students. And then on the income lens, we have students who are eligible for free or reduced lunch. So we'll refer to those students as FRL students. And you can see on the right, we have a map illustrating where the focal students are in the San Francisco district. And just to note that this definition might be adapted as we continue to iterate in the future. Awesome. So this brings us really well into our project goals. So number one, we hope to design an equity tiebreaker for elementary school assignment. I wanted to highlight the fact that this is for elementary school assignment, and that's really important in the context of equity, because a lot of times elementary schools set up the educational trajectory of where students will go to K-8 school and high school and beyond. So we want to improve the equity in terms of outcomes early on in children's education. Which leads into my next point, improving equity and access, especially for focal students. So we really want to see that focal students are assigned to one of their most preferred schools. Lastly, we mentioned that the Ctip1 tiebreaker struggled with certain areas. And so we hope our policy, in contrast, is interpretable, transparent, and flexible. We hope that it will increase trust between communities and families and the San Francisco School District. So to illustrate that, we also have some text from the board policy itself, which says that a tiebreaker based on students' residence where individual student demographics will not be considered. And that is for two reasons. So first, the district wants to protect student confidentiality and avoid using sensitive and confidential information. And secondly, this works to make the system more honest and fair for everyone, because if we focus mostly on individual data, that could leave room for people to try and game the system. So we hope to make it strategy proof. Awesome. And now I'll hand it over to Gabriel, who will talk about our methodology.
Right, thank you, Ria. So yes, now we'll talk a little bit about how we designed this equity tiebreaker. So our process was very iterative. We start by getting from the district this definition of focal students. Then we are able to design new tiebreakers. Tiebreakers are essentially classifiers that act on the set of blocks, because as Ria said, we are not classifying individual students. The tiebreaker is gonna output for a block a label of focal or non-focal. Those classifiers, they might have some parameters we need to optimize. And for that, we're gonna look at some statistics of the classifiers, such as the accuracy and the recall and the false positive rate. But however, what we really care about is whether the tiebreaker helps students get into school. So for that, we have a choice simulator provided to us by the Stanford research team that computes the utility of the school and the zone for a family and generates a preference list for the student. With that, we can then run the deferred acceptance algorithm that Ria explained and get an outcome for the school assignment. We do this process a few times because there is a lottery factor and average the results. We also would like to make sure that our tiebreaker does not exacerbate gentrification patterns. So we compare the tiebreaker assignment with current gentrification maps and summarize these results. So after we have all of that, we communicate to the district and get their feedback to design a new tiebreaker that is adapted to what they need. This feedback usually revolves around improving interpretability and also incorporating new features or removing some features from the tiebreaker design. So let's explain a bit why classifying blocks poses interesting problems for us. There's a hypothetical scenario in which San Francisco has 4 blocks, A, B, C, and D. The yellow faces here correspond to focal students, students that we think deserve an equity tiebreaker, and the purple faces correspond to non-focal students, those that don't deserve an equity tiebreaker. Blocks A and D have an easy classification because they are 100% focal or non-focal. So we think that they should receive the equity tiebreaker in case of block D and don't receive the equity tiebreaker in case of block A. But blocks B and C have a more nuanced classification. And however we choose to do that is going to affect our performance. For example, if we select blocks B and C to both have the tiebreaker, then all the focal students are going to receive the equity tiebreaker. But those 6 non-focal students here who don't deserve an equity tiebreaker are also going to receive it. We call those the false positives, non-focal students with an equity tiebreaker. If instead we don't give a tiebreaker to blocks B and C, then we don't have the false positives, but we're going to introduce a problem in the focal students that are in those blocks. Those focal students, they deserve an equity tiebreaker, but don't receive it. Those are called the false negatives. Intrinsically, most blocks in San Francisco are actually very heterogeneous. That means that most blocks are going to be in the situations of blocks B and C. In fact, the median percentage of focal students in a block is around 20%, excluding, of course, the blocks of very easy classification that don't have any focal students. So we actually expect that in order to target a lot of focal students, we are going to have to also target a lot of non-focal students. And this trade-off cannot usually be solved by optimization methods because you need a qualitative input. So we usually need this part to ask the district, what is the false positive rate they are comfortable with? Or what is the number of mistakes they are comfortable with making in their policy in order to reach the most number of focal students? Based on that, we can build then a benchmark tiebreaker. The benchmark tiebreaker is very simple and just looks at the demographic composition of a block based on the definition of focal students we work with. If the block has enough focal students, it receives a tiebreaker. If it doesn't, then it does not receive the tiebreaker. Enough is defined based on a threshold that's inputted by us at every step. Usually this threshold can be given as either an absolute percentage that the block has to meet, but it can also be given as a cap in the number of students that receive the tiebreaker or as a cap in, for example, the false positive rate that I mentioned before. However, after talking to the district, we were told that this tiebreaker does not encompass all the nuances of the policy. Because, for example, some blocks might have a lot of focal students under the current definition. However, those focal students live in a very developed area that has access to a lot of urban resources, such as public transportation. Whereas there are many more focal students who live in areas that are poorly served in these terms. So we consider that there's a step before qualifying the blocks for the tiebreaker, which is the eligibility step. The eligibility step will ask whether a block is even eligible to be considered for the tiebreaker. If the block is eligible, then it goes through this qualification process, and if it meets the threshold, it receives the tiebreaker. Uneligible blocks are never able to receive the tiebreaker. Currently, we are working with two definitions of eligibility. Either a block who was in a previously redlined area of San Francisco, or a block that has a public housing project are eligible for the tiebreaker. So if the block meets any of those two criteria, not necessarily both, it will be eligible for the tiebreaker and it can go through the qualification process. If it doesn't meet either of these criteria, it does not receive the tiebreaker automatically. We chose those two criteria for eligibility because they reflect the policy text the most at this point. This is a line from the original policy. It says that the equity tiebreaker will be applied to applicants who either reside in federal public housing or in historically underserved areas of San Francisco. So we identify those two public data sets, one of the federal housing projects in San Francisco, and the other, the historical map of homeowner loan corporation grades for San Francisco, or the redlining map, that represent underserved communities and that can be fed into the classifier so that we can classify the blocks and give them a tiebreaker. And furthermore, we don't have to delve into the further considerations that we had that much now, but our methodology is very flexible, so we can incorporate different eligibility and qualification criteria. And as I mentioned, we were also trying to incorporate gentrification. And here's the data set that we use for that, so you can have an idea of how it looks like. It's a data set from UC Berkeley's urban displacement project. Perfect. And oops, sorry. And now I'm going to pass it on to Juan, who's going to discuss our main results.
Thank you, Gabriel. We can go to the next slide. Well, the first thing we want to talk about is how evaluating results. I want to focus on this plot on the right. We have in the y-axis the proportion of focal students receiving the priority, and on the x-axis the proportion of non-focal receiving priority. And here we plot our three equity tiebreakers. We have the benchmark on the blue line. We have our proposed benchmark equity tiebreaker with the green line, and then we have the Ctip equity tiebreaker on the dot. Since we can like frame this issue, this problem of assigning equity tiebreaker as a classification problem, it only makes sense to tune and evaluate the models this way by looking at the true positive rate, which is the y-axis, and by looking at the false positive rate, which is the x-axis. But since this equity tiebreaker is going to be participating in, or is going to be part of this really complicated assignment process, it's also very important to use counterfactual simulations to make sure that the equity tiebreaker is actually achieving what we expect or we intended to achieve. So that's why we use the Stanford's research team simulation engine to run simulations. And in order to be able to compare and to see how much of a difference our proposed equity tiebreaker does compared to the benchmark or the Ctip, we chose instances of all three models that have approximately the same false positive rate, in this case at 16%. And we also simulated the case where there's no equity tiebreaker. And an important part before going into the results of how the equity tiebreaker affects ranks is to look at how the equity tiebreaker is distributed or materializes in the San Francisco map. We have the Ctip that is very coherent and is very targeted to places that have been historically underserved. And then we have the benchmark that clearly is optimizing which blocks get it and not in order to maximize the true positive rate at a given false positive rate. And then finally, we have our proposed equity tiebreaker, which seems clearly like a mixture where it has some granularity in terms of targeting specific blocks or block groups, but it also has this coherence where it targets the historically underserved neighborhoods or parts of the city. Yeah. Then another check we wanted to do is see what was the distribution of the students receiving the tiebreaker for the simulation. For the simulation, we use student data from the 2018-2019 assignment process. We can see on the table on the left that the false positive rate of all the three methodologies we're trying to compare is relatively similar. And we can see that the true positive rate is as expected, is the lowest is for the Ctip1 and the highest is for our benchmark model. We also want to remind you guys that the focus students are the students who are both ALPI and FRL. We also here define an extended version of the focus students, which is those students who are either ALPI or FRL students. And for that case, when we are comparing false positives, true negatives, and all those, we also decided to define a new kind of like status or category, which is the extended positives, which is students who fit the extended focus student definition and are also receiving the equity tiebreaker. Yeah, and now to get into the results, kind of the big question is, are students better off by getting the equity tiebreaker? So here we're plotting the average change in the rank of assigned program. The average change is computed in comparison to the case or the scenario where there is no equity tiebreaker, and it's an average change because it's average over 20 simulations for each student. Positive changes means that students are getting they're getting worse ranked programs, and negative changes means they're getting better ranked program. And we can see here that all the students who get the equity tiebreaker, that's the true positive, the extended positive, and the false positive, are doing much better than those students who don't get it. And then we decided to look at, but there we were looking at students who were getting the tiebreaker, and we need to like keep a focus on the total focal population. So we group them together, and here we show the focals, which are the true positives plus the false negatives, and the non-focal, which are the rest. And here we can see that the effect of the equity tiebreaker on the overall focal population is more hard to interpret. And we can see that there's some students who do better and some that do worse. And with the benchmark method and with the proposed equity tiebreaker, we can see that a majority of students are doing better under the the equity tiebreaker. And finally, we wanted to take a look at kind of like what are the distribution of the actual rank of the assigned programs for the focus students who get the tiebreaker. So here we track what's the rank for the students who got the tiebreaker under each of the methodologies and what was the rank they were getting under the scenario where there's no equity tiebreaker. And we can see that under all three regimes of equity tiebreakers, focus students who get that tiebreaker do better, and a great majority of them get one of their three top choices. So yeah, so a quick discussion of results and limitations. Our equity tiebreaker improves the focus students' school choice. We could see by analyzing the improvement of students who got and who didn't get the equity tiebreaker. However, when we look at the improvement of focus students in general, we see that the improvement is small on average, and it's hard to like identify the impact. We have some hypotheses of why this is happening. This is concerned to the fact that the policy uses guardrails, and therefore students only compete with other students in their same diversity category. And as we can see in the plot on the right, the second diversity category, or diversity category number 2, concentrates has around 40% of focus, focus students, and has around 40% students receiving equity tiebreaker. So the effect that the equity tiebreaker can do within that diversity category is limited due to the fact that a lot of students have this priority. So that kind of like means that maybe the number of focus students is too large. And yeah, now I'm gonna hand it back to Ria for the conclusions.
Awesome, thank you. Yeah, so now I'd like to talk about like our overall contributions. I know we went into some of the more quantitative results, but qualitatively, to summarize, over the course of this program, we helped develop an equity tiebreaker that is interpretable according to the SFUSD policy, because we work to directly translate that text into like our assignment and algorithm design. It's also transparent because it's really clear the relationship between the focal students and equity, rather than equity and test scores with Ctip1, and not gameable because we're using the blocks rather than individual student data. Lastly, we believe our tiebreaker is flexible to the changes in groups of focal students because we can shift our definition of focal students. Also, our code is really well documented and easy to play around with to adapt to various changes. So overall, our tiebreaker performs well when compared to a benchmark model or to the current Ctip1 process. Because focal students receiving a tiebreaker see an improvement in their assignment outcome, and more focal students are reached than under the current or existing process. So as I mentioned, we documented all of our analysis in an interactive and dynamic notebook that SFUSD staff can experiment with to adjust parameters and continuously iterate to improve the process. And this brings us to our future work. So firstly, we hope to define focal students continuously in like an iterative manner, perhaps narrowing our definition of focal students to understand how we can really target the students who are the most underserved by the district and who would need that priority in student assignment. Community feedback can be incorporated and continuously weaved into the design of the tiebreaker. We've been working with the SFUSD engagement team to hear their thoughts and make sure we're integrated with the community and their perspective, because we really do believe that parental and family buy-in is really important, and that it's great to be on good communication terms, making sure everyone understands and fully gets behind the tiebreaker itself. So another thing that we're hoping to expand onto in the future is addressing gentrification issues more coherently and cohesively, just because of how gentrification will cause demographics to change as wealthier individuals and families move into low-income areas and perhaps displace those residents. Then that changes the dynamic of which blocks we would like to give equity tiebreakers to. Lastly, the tiebreaker is going to need to be incorporated into the rest of the assignment process. So school zone decisions may influence the tiebreaker eligibility process, and guardrails or diversity categories limit the ties of students to the same diversity category. So that's all we have for today. Thank you so much, and let us know if you have any questions.
Thank you for the presentation. Awesome work. There is a question in the chat. What is the trade-off you and SFQSD made between false positive and false negative?
Yeah, we can, Juan, do you wanna talk about that in the context of the simulation, or? I can also. So, as Juan mentioned in this slide, we wanted to compare the tiebreaker outputs to the Ctip, which is the currently implemented tiebreaker. So in order to actually compare and see how they performed under the same circumstances, we'd like to keep the false positive rate constant across the tiebreakers that we are testing. So if you can see here, Ctip was just a point because it was just an instance of the tiebreaker that was realized throughout the last years. So Ctip was operating under like 18% or something false positive rate, and I think we have the 10%. Sorry, a 10% false positive rate. So we try to keep the false positive rate somewhat constant across the different tiebreakers that we're testing. And in this way, we could have we show that we could actually have a much higher true positive rate for roughly the same false positive rate for the tiebreakers that we were proposing. So that shows a comparison to Ctip that we can improve under the same circumstances.
Yeah. Also, also to answer the question, I don't know if you can hear me, but I think the San Francisco Unified School District didn't make an analysis of like what's the trade-off between false positives and false negatives. These are criteria we kind of like looked into as we were looking at the problem and trying to formulate this as a classification problem. But so we are like, it's us who started talking about false positives and true positives and using it as a tool to select models.
Great, thank you for the answer. Are there any other questions by our panelists or audience? If not, I have one last question. Maybe you mentioned it and I missed it, but I was wondering, what is the impact on the non-focal students? Like, how are their choices affected?
Yeah, I don't think we selected it. I mean, there's a slide where you see the effect, and it's basically, so the effect is mostly on the students who, yeah, so that in that slide, we can see that like the non-focal students did some change, but both in both directions, and yeah, so it's just.
Yeah, I mean, in terms of, yeah, their rank. Okay, I see.
Yeah, so we can see in this slide that obviously, you know, in order to improve the rank of some students, you have to decrease the rank of some students. So the change being positive means that the ranking of the school increases, which is bad for the student. Notably, you know, the rank doesn't decrease as much as it increases for the students that receive the tiebreaker. So the rank on average decreases to 0.5. And the rank increases on average by 1.5. So there is a higher increase in rank than a decrease. We do note that false negatives systematically have they are even worse off than true negatives. So we were operating under the different assumptions that the utility model makes to assign the list of preferences. And that might also have to do with the fact that some focal students live in neighborhoods that the schools and that they could list in their preference have a different utility value for them. And this is also, the rank is a discrete quantity. We didn't get a chance to examine the change in utility, but that, but that would be another step of doing it so that we could have a more continuous version of this type of. Yeah.
I see, thank you. Any other questions? If not, let's thank all of our teams again. Thank you to the audience for attending the special seminar by Stanford Data Science. This Stanford Data Science for Social Good will wrap up this Friday. And we were excited to have all these fellows at Stanford, at least like virtually this summer. And we are looking forward to the future iterations of the Stanford Data Science for Social Good program. Thank you and bye.